back in Strasbourg, I'm doing so fast in computing. So for me, it's no use to do it. So it's better to say, oh, could you do this in 3 minutes? This is done. So I don't have to learn. So it's very convenient. You know, if you do something with computing, you could be an expert. It takes time. But if you have a good computer and can do it for you, then you are safe. So this is what happens. And so the first step, look at this. All positive, no problem. With integral coefficient, which is, the same for, this is for tangent. And of course, when you plug q and t equal 1, let's do it in here. When you plug t and q equal 1 here, you get 16. 16, and here 272. So T711 is 272. Okay, now the problem is prove that those coefficients are polynomials with positive integral coefficients. Okay, so now let's go back. In other words, we simply have this. So it boils down to that identity. So let's form it. I could have started my talk with this identity and say, prove that E2 and TQ is a polynomial with integral coefficients. The same. And how can we do it? Well, in the case of secant of Q, tangent of Q, this is easy because you just take the differential. You just take the differential properties of secant tangent, Q mimic. So in other words, you take them and you do the Q calculus with the same, and you have all kinds of identities. Everything is positive. That's very easy. But in that case, but in the previous case, we don't know. You see, those are the coefficients that are defined here, and we do not have binomial identities of some kind to work with those coefficients. Oh yes, Q differential property of secant tangent using the Q binomial theorem dear to Ligatsky. You see, so this is a corollary of the Q binomial coefficients, but not in the new case. Well, in that case, we have to go back to old mathematics and to what people have done in the 19th century. So we have to go back to what Zeilberger had done. Surprisingly, it was a great surprise that this old-fashioned model in combinatorics was really the model to be used for this particular case. So Zeilberger introduced the concept of zigzag permutation or alternating permutation. So I guess, okay, that's it. Huh? So it goes up and goes down. And what he proved that the number of alternating permutation of order n was equal to either the secant number, if n is even, or the tangent number, if n is odd. So this is no result, and surprisingly basic for studies. And well, this is also this is the Q version of André, and not difficult either to prove. You see, as soon as you have André, you change the binary coefficient by the Q binary coefficient, and it works. For a number of inversions, it's easy, but it's not what we need in here. So this is a case of this is the even case, but what to do with the variable t? Okay, so let me start with some definition. Not very many, there will be 3, but very classical. And you will see immediately why we should introduce those 3 definitions. So suppose we have a permutation written as a linear word like this. And let me define I dash. I means inverse, dash descent. So I think maybe I could give an example. Okay, let's have an example. You have a permutation of this, like here. And whenever I plus 1 is to the left of I, whenever I plus 1 is to the left of I belongs to the I dash, right? So 5 is to the left of 5, 9 is to the left of 8, and 4 is to the left of 3. So the set of I dash is 1, 3, 4, and 8. So I dash would be the number of those, the cardinality of I dash, the number of I descent. If you're familiar, you know this is simply the number of descent of the inverse of the permutation. But don't worry, it's better to say this. And I dash is the sum of those. So 1 plus 4 plus 8 plus 3 is 16. So the only thing to remember is, in fact, we don't have to remember it. So we have the statistics based on the set I dash. And, well, try I dash. We know this. We know that those two genuine functions are equal. That's, let's put it this way, traditional result. That it is contained in good books. Richard, is it in your book? Yeah, you say.
But then the result is the best proof.
No. This is not the topic of my talk. Okay, so so let's prove it 4 equal 4. You say 4 equal 4, you have 5 permutations, right? Okay, I match means 3 is to the left of 3 to the left of 2. Yeah. Okay, so it's 2, 3. Yeah. 4 is to the left of 3, and 2 is to the left of 1. So this is 1 plus 3 equals 4. And you see this? Oh, yes. So we have the proof for equal 4. So it used to be called the British proof. See? The British proof said that it's true for equal to 4. And you by extension it's true for all right. And so we have A for Q equal to this. Okay, and now the most general, the most obvious statistic you could associate with I dash is I dash. For obvious reasons. Well, but it's not true, but 1 plus I dash does the job. And this is what we do. So, and it works. Okay, now it works, you have to prove it, you see. I'm not going to prove it. But now we have found the 2 necessary statistics to prove that it is positive. Yeah, you know, what's good, my chairman is not there. But I will stop soon. Okay, so now I reach the thing I want to state, that the coefficient of tangents of Q, so no, well, those two polynomials are genuine polynomials by 1 plus I dash and I dash. So accordingly, those polynomials have positive integral coefficients. Now, to just say, before my chairman comes back, okay. Now, the only thing we have at our disposal are those 2 identities. It means what? It means that if we want to prove this, we have to plug the new combinatorial definition in here. And what? You know, in the language of Doron, I would say, you have to find guys, and bad guys, and good guys, and you have to kill all the bad guys. But now the next step is to work out sine inverse involution in such a way that when you apply it, you get